Hello everyone, welcome to Educative RKIS. Today's our topic is work energy theorem or work energy principle. According to this principle, work done by the net force in displacing the body is equals to change in kinetic energy. Okay, so let's see the proof of this theorem. Suppose I have a body having mass small m. If I apply a force F on it and it covers a distance S, is having an initial velocity u and final velocity small v. So if we calculate the small amount of work done in this case, so dw is equal to fds, and we know that the dot product of two vectors is fs cos of theta. So dw is equal to fds cos of theta, as the both the quantities force as displacement, these are vector quantities and these are also dependent upon the direction. So they both the quantities are acting in the same direction, that is in the right direction. So the angle between them is 0 degree. Force is also acting in this direction and displacement is also acting in this direction. So the angle between them is 0 degree. And we know that cos of 0 degree is equal to 1. So I put the value of cos 0 is equal to 1 in this equation and I'll get dw is equal to fds. According to the Newton's second law of motion, we know that force is equal to mass into acceleration. So I will put the value of force is equal to mass into acceleration in equation number 1. Here the work done dw is equal to m dv upon dt, because we know that acceleration is the derivative of velocity with respect to time into ds. If I take this quantity ds upon dt, then we know that the rate of change of displacement is just nothing but velocity. So here dw is equal to m v dv. So dv. So here dw is equal to m v dv. Here if we integrate this is a small work done, and if we want to calculate the complete work done from this point, let's say this initial position to final position, so what we have to do, we have to derive what we have to integrate the velocity derivative, this derivative from the lower limit, that is having initial velocity u, to the upper limit, that is having velocity v. So here integration of dw is equal to mv dv with integral value lower limit u and upper limit v. So here the integration of dw is w and mv dv, because m is a constant, so we will take it outside, and u into to the lower limit is u and upper limit is v. We know that integration of x raised to our n into dx is equal to x raised to our n plus 1 upon n plus 1. So here in this case we have an integration w is equal to m v square upon 2 into d into this bracket, and having lower limit u and upper limit v. Okay, so we will put the value first in the upper limit minus lower limit. So w is equal to m v square upon 2 minus m u square upon 2. So this is just nothing but work done is equal to, this is the final kinetic energy final minus kinetic energy initial. Hence the net work done in displacing the object by this force F from initial position this to the final position this is equal to the change in kinetic energy, that is the final kinetic energy minus initial kinetic energy. We know the formula of kinetic energy is half mv square minus half mu square. Thank you.